Okay, so let me share my my terminal. In this short demo, I would like to show how we can apply the concept that I just showed you in my slides to a very simple operation. So let me. Okay. I will show you the solution of an exercise we generally assign to students during our Cineca courses. For example, if during September we will start with other courses, which are HPC courses, which are free, and so you can have a look at our offer. And we also make GPU programming courses, and we will see this material. They are held in English. And during these courses, we also present some, we give students some exercise. For example, this exercise is a very simple application of the stuff we just see. So we have to process two arrays. We have to combine the data of two arrays, array A, array B, into another output array, the array C, okay? If we have to do this in CUDA, we can port this code simply allocating a counterpart array A, B, and C on the device side using CUDA malloc, for example. Here are CUDA events just to measure the time and to measure the efficiency, the speed up that we gain moving this computation from the CPU side on the device side. So it is not very interesting. So, for example, we copy the data from the host buffer A and host buffer B into the device buffer A and buffer B. So we have moved data. These are all blocking operation, as you can see, CUDA man copy. They are blocking operation, no asynchronous. There is a kernel launch. This is an asynchronous launch, so the control will come immediately back to the host, which is the immediately following instruction is a CUDA man copy. This CUDA man copy, if not explicited in other way, is given all these operations, the CUDA man copy, the kernel launch, the CUDA man copy, they are pushed into the default queue. That is the stream 0, okay? And they will be executed in order, okay? So there is no concurrency here. So the CUDA man copy, which will transfer the DC buffer onto the H host buffer, will take place just after the array, the kernel array function has completed, so that the DC buffer, which is the output of this kernel, is filled with the right data. Okay, so this will take just after this. And since this CUDA man copy is a blocking copy, this other operation here will not take place until the CUDA man copy is finished. And the CUDA man copy will not start until the kernel is finished, and so on, backward, okay? So this is a very basic example. If I run this, this is an example in which the kernel is basically a simple transformation. I take an element of the eData array, I multiply this data with an exponent of another data, another buffer, the J buffer, okay, which will make the argument of the exponent. So I combine these two input data into something else, and I store them on the output buffer, okay? I repeat this operation, for example, 100 times. This is useful to adjust the length of this kernel, okay? So I can adjust how much the kernel will take to run these simple operations, okay, with respect to the data movement, okay. So the array to be computed is 2 gigabyte elements long, okay. So we have 2 million elements to transform with this simple operation, okay? Now, let me compile this example and run it, okay? Sorry. Okay, I have 2 million elements to be transformed, as you saw. This transformation has been decomposed into 8,192 blocks of threads, and each block of thread has 256 threads. Each thread will act on a different element of the array, okay? So once all the thread has executed their work, their kernel, the output will be put onto the D_C buffer, and then we take back it on the host. If we measure the total amount of time which is composed by the host to device movement of the 2 input array, the kernel launch, and the device to host movement of the results on the device, this takes almost 3 milliseconds. The same computation, exactly computation performed of just one core by just one thread on the CPU takes 2 seconds and 0.8, okay? So it is almost a 1000x improvement in performance, okay? Now, let's evolve this exercise, which is all serialized, with stream in an asynchronous way. Here, I choose to use chunk of data of this size using 8 streams, okay? So in order to pipeline my computation, remember that I have to put my original data on the host, not on standard buffer, but on pinned memory. So instead of using the standard C malloc, I use the CUDA malloc host allocation to allocate the initial data. I initialize my data. Then I start my loop on the number of chunks I want to subdivide my original data. And for every chunk, with this function, I just compute the start and end index of my original host data to be processed for each chunk, okay? I will push in my stream, my I stream, chunk stream, the movement of input data DA and DB, I launch my kernel in an asynchronous way on this stream, and I push back, get back, sorry, the data. Okay? As you can see, there is an event record here and an event record start here. This event can be used to measure the lapse time. This is what I use to measure how much does it takes to run this code. If I run this code, this is just one GPU. This is the original run. If I run the second version with stream, here you see that I have almost a 4 times less execution using pipelining with stream. I can, of course, go further and try to use multiple GPUs. So now I can go beyond one GPU and use multi-GPU. Here I should anyway declare the streams for each GPU. So I will end up with, for example, an array of array because of streams, okay? Because the first index select the GPU and the second index select the many streams that I have activated on that particular GPU, okay? Malloc cost, starting with a pinned memory. I ask how many GPU I have available on my node. Then for each GPU I loop over the GPU, I allocate memory on that GPU to host, let's say, to host that particular data for each stream. Then I will loop over the GPUs and over the chunk of data that each GPU has to transform. Always with asynchronous memory movement, kernel function, and data retrievement. If I run this one, I should take also, again, better result. This is not the case, as you can see, with respect to the second, because, as I said, in this case, the length of the kernel is too short. Let's say the kernel is so short that it takes more to data movement to take place with respect to the kernel. But if I improve, for example, if I improve the length of the kernel, so instead of repeating this kernel 100 times, I repeat it 1000, and I do this both from the stream-only version and on the stream plus the multi-GPU version, you will see that I will have an improvement. One GPU, 6 milliseconds with streams. 4 GPUs with streams, 2 milliseconds. Okay. I have not time to show you the profiling, which would be also a nice thing where you can really appreciate the overlap. Let's say this is the overlap of the execution, the blue kernel with the violet and green blocks of data movement. As you can see, they are all in overlap. And if I expand this, here you can see the 8 streams that I have used to pipeline the operation of data movement, kernel, and data retrievement. and they are interleaved between all the streams in the order that the device scheduler choose to be the best for the runtime of this runtime. But it ends up with this operation. If you see the exercise 3 with multi-GPU, you will see that there are several GPUs now, 1, 2, 3, 4, and all of this is used with the streaming. This is the smaller kernel part. This is the longer kernel part, and as you can see, there is almost full overlap on the, I would like to okay. There is almost total overlap of kernel execution blue line on the GPU 0 with the kernel execution blue line on GPU 1, GPU 2, and GPU 3. And all the other stuff, the green and the violet, are data movement and retrieval. So this is the maximum efficiency that you can achieve, for example, on this node with this task with 4 GPU and multiple stream. So I hope you enjoyed this talk. And if we share the slide, you have my email on the first slide, so you can contact me if you have other questions, and that's it. Thank you very much.
Thank you, Luca, for the great presentation and demonstration. And as you said, considering the lack of time, if you have any questions, please contact the speakers by mail. And I wish to thank all the speakers for the interesting presentation and the participants for taking part in the workshop, and hoped it fulfilled your expectation. And as I wrote in the chat, you will be notified as soon as the slides and the recording are available on our website, EuroCC Access. And thank you again, and see you at the next workshop. Bye.
Bye. Bye-bye.
Thank you so much, Martina. Bye.